So what we're going to prove here is that the sine of an angle is equal to the opposite length divided by the hypotenuse. We're going to do that using similar triangles. So what I want to do first is draw a triangle out on the unit circle. So we'll grab a right triangle. Okay, so let's draw our unit circle in here. Okay, and now let's draw a triangle. So we've got a right triangle, and we're going to call this angle in here theta. Now here's what we know. We know that the hypotenuse length right here of the triangle is 1 unit long because it's on the unit circle. We also know that this point from the intersection of the terminal side and the unit circle is going to be cosine theta comma sine theta. This is the important part here, the sine theta. So what we know is that this length right here, the one going vertical, is sine theta. So whatever theta is, if theta is 40 degrees or 80 degrees, the sine value of that angle represents the height of this side. Okay, that length. So let's take that triangle and let's pull it off over here and just redraw it so it's a little bit bigger so that we can see it better. So that triangle in there has an angle here of theta. It has a hypotenuse length of 1, and its opposite side has a length of the sine of whatever this original angle was. Now if we take any other triangle that's either bigger or smaller, I'm going to use a drawing that's bigger, okay, but you can do one that's smaller too. If we take another triangle where theta is the same angle, so same angle, so this angle is the same as this angle. We also know that if we're creating a right triangle, that this angle is the same as this, and therefore those last two angles up top here, so this angle up here and this angle here, are also the same, which makes these two triangles similar. Since the two triangles are similar, the ratio of the sides are equal to one another. So here's what I can say. I can say, by the way, this triangle over here is our arbitrary triangle. So we'll just call this H for hypotenuse, and this over here O. So this is an O. I'll draw it a little bit bigger here. So over on this side, that's O, standing for opposite, and this is H for hypotenuse. So I'll put H and O. So if I take the ratio of the sides, if I take 1 and divide it by H, that should be equal to sine divided by O. So the sine of theta divided by O. That's not 0, okay? Divided by O. Now, if I just multiply both sides by O, so we'll do that here, then O cancels on the right side. And on the left side, I have, well, this is really O over 1. So when you multiply fractions, top by top, bottom by bottom, you get O over H is the sine of theta. And that's what we want to prove. We want to show that the sine of an angle is equal to the opposite side divided by the hypotenuse. And if you're used to seeing the SOHCAHTOA, and we'll explain that maybe later, or I'll link you to a video or something, but if you think about SOHCAHTOA, okay, this first part of SOHCAHTOA stands for sine is equal, so sine is equal to opposite over hypotenuse. And so that definition for SOHCAHTOA, sine being opposite over hypotenuse, comes from using similar triangles and taking a larger scaled up version of a triangle off of the unit circle.